Light switch for sight, WAChR, and the future of gentle optogenetics. Imagine restoring vision not with lasers and implants, but with ordinary light from a lamp. That's the promise raised by WAChR, a newly discovered ambient light-activated ion channel that could transform how scientists approach sensory restoration. In the long quest to bring sight back to people blinded by retinal degeneration, the prevailing tools have been powerful but cumbersome. Traditional optogenetics relies on engineered proteins that respond only to intense narrow-beam light, usually delivered via specialized devices. The WAChR discovery comes from a team at Science Corporation, a biotech company based in Alameda, California. They used AI-guided protein engineering to create WAChR by mutating an existing opsin called WiChR. WAChR changes the equation. It's a natural, light-responsive protein that, in lab models, opens in response to everyday light levels. Think desk lamps, sunlight through curtains, or a flashlight. If this works in humans, it could mean that neurons once silent could be awakened simply by turning on a light. What is WAChR really? WAChR, short for a wide ambient light-activated channel rhodopsin type receptor, is a light-sensitive channel discovered in certain organisms and now repurposed in experimental vision research. Channels like WAChR reside in the membranes of cells and permit ions to flow when activated by light. This ion flux triggers electrical signaling, the currency of neurons. Crucially, unlike many synthetic optogenetic tools that require intense wavelengths from lasers, WAChR responds to broad, lower-intensity light, closer to what humans encounter daily. That gentler activation is not just convenient, it potentially sidesteps the heat generation and phototoxic stress associated with high-intensity stimulation. How this could translate to vision. Our visual system depends on a cascade of events. Light hits photoreceptors in the retina, those cells convert photons into electrical signals, and that information is passed to the brain. In conditions such as retinitis pigmentosa or AMD, age-related macular degeneration, photoreceptors die, but much of the downstream network, including the optic nerve and visual centers in the brain, remains intact. Rather than replacing damaged tissue with hardware, the WAChR approach aims to reintroduce light sensitivity into surviving retinal cells. Using gene-based techniques, researchers seek to enable these cells to respond directly to ambient light, allowing them to generate electrical signals once again. Those signals can then travel along the existing visual pathways to the brain, producing a basic but meaningful form of visual perception. This is not instant high-resolution color vision. Current data suggests the potential for edges, motion, shapes, and contrast, similar to early stages of visual perception. For many, that represents a transformative leap, detecting doorways, reading large print, or perceiving movement in the environment. Why it feels so different. Optogenetics has always held enormous potential, but it's been tethered to complex hardware and intense light sources. WAChR introduces two appealing departures. Ambient activation. Ordinary light suffices. No invasive implants. No hardware buried in or near the eye. Those traits could make gene-based visual restoration more accessible, safer, and far less intrusive. Balancing hope with risk. It's important to temper excitement with clear, science-based caveats. Off-target gene effects. Gene therapy carries inherent risks. The vector might insert the WAChR gene in unintended cells or genomic regions, potentially disrupting normal function. Regulatory agencies require exhaustive characterization of these effects before human use. Phototoxicity and light sensitivity. Although WAChR responds to ordinary light, long-term exposure to any light-activated protein raises questions about cellular stress and photo-induced damage, especially in the delicate retinal environment. Safety studies must examine whether chronic activation could harm cells over time. Neural integration and interpretation. The retina and brain interpret signals in highly complex ways. Even if WAChR can make cells fire, the brain must learn to interpret those signals meaningfully. That neural plasticity is unpredictable and varies across individuals. Clinical timeline realism. Current work in animal models demonstrates proof of principle. Researchers often cite human trials in 2 to 3 years, but that timeline assumes smooth progress in safety testing, manufacturing, and regulation. A sourced qualifier, such as approval time lags and required phase-by-phase safety endpoints, grounds expectations more realistically. Where things stand now. In animal studies, WAChR expression has driven observable responses to ambient light. Mice with engineered retinal cells have shown measurable neural and behavioral reactions during light exposure, a promising sign that WAChR can function in a living system. However, translation to human retinal physiology is non-trivial. Human retinas have more complex circuitry and integration with central visual pathways. Demonstrating robust, reliable, and safe vision improvement in humans will require cautious, staged clinical trials. Looking forward, if WAChR fulfills its promise, it will not only broaden the practical reach of optogenetics, but could also pioneer gentler neuromodulation techniques across neuroscience. For people living with blindness today, WAChR offers a reasoned optimism, a future where the difference between darkness and perception may come not from lasers, implants, or prosthetics, but from ordinary light and precise biology. In this evolving field, the next few years are likely to determine whether WAChR is a turning point or a stepping stone toward even more refined biological interfaces. Reference: an invitation. Join me on Monday, 26th of January 2026 over lunch to discuss this and other issues related to nutrition and health. Full details are as follows. Day and date: Monday, 26th of January 2026. Time 12:30 to 14:30 hours. Venue Cafe MAB. Address Malaysian Association for the Blind, MAB. Jalan Tabing off Jalan Tun Sambanthan 4 Brickfields, 50470 Kuala Lumpur. Attendance. Attendance is free of charge for all persons with disabilities, PWD holding an OKU card. However, places are limited and depends on donations and sponsorship received. Donation attendance is by donation for able-bodied and sighted participants. Minimum donation is RM20, which should cover your lunch as well as for one PWD. Any balance will go towards my various eye treatments.